project overview, constraints, challenges and risks,
That's right.
approach, summary, and references. This slide shows our abstract and give a brief introduction about our project. Please feel free to visit our website for the updated abstract. Why the heart flow chamber? The cardiovascular diseases is the leading cause of death in the United States, and in 2008, according to the US Census, around 600,000 people die every year because of the heart-related diseases. And the most of these diseases happen because of the valve issues, especially the mitral valve issues. This valve is located between the left atrium and the left ventricle, and its function is to preventing the backflow of the blood, and the missing of this function will cause a regurgitation and prolapse of the valve. The patients are replacing their valves with the mechanical valves. However, because of the shearing stress, the shearing rate of the blood flow, a biological components will build up on the materials of these mechanical valves. So we decided to design a device will be able to test the build-up. These are our project overview. You can see the flow parameters. We're figuring out the flow parameters in the beginning, then development and specifications. We validate the design, and with the help of the SolidWorks and the ANSYS, we will be able to build our prototype. Then we did the testing until reaching the final design. Our constraints are the flow rate, which is 1.2 liter per minute, and the Reynolds number in the flow chamber must be the same as the one around the mitral valve. The height and the width of the gasket has to be larger and greater than 200 micrometer because of the size of the white blood cells, which is the largest blood cell. For boundary layer thickness, this is in our calculation, it should be less than 1 micrometer. These are our non-technical constraints. So we decided to use the maximum fund provided by the school, by the Temple School of Engineering, which is $500, and we are successfully maintaining this so far. That time we already built our prototype, and we already done with the testing. So we are expecting the time as a non-technical constraint. We made most parts of our prototype from polycarbonate plastic that's helped us to use it for so many times. And we used special machines to cut the different small parts of our prototype. Choosing the materials, we choose the material that's strong enough, to be strong enough, that's carry the high pressure, and to be transparent, so we can use it, so we can use our device under different microscopic lenses. During the different steps of building our prototype, we faced a couple of technical challenges. To avoid having air bubbles in our prototype, the chamber has to be filled, wetted, and degasked. And since we are dealing with the blood, which is a very expensive solution, the dimensions of the gasket should be very small to reduce the flow rate and to reduce the cost of every test. We are having a risk of leakage, so that's why we had to find a good material to seal different parts of our device together. To start with the design, we had to use SolidWorks to design the different parts of our flow chamber. Here you can see the parts of our flow chamber. The first part is the top part. It has two holes representing the inlet and the outlet, and you can consider this part as a cover of our device. The second part is the gasket. This part have dimensions. This part determines the volume of our flow chamber, and these dimensions mimic the dimensions of the mitral valve. And the third part is the bottom part. So this part where we will be located for the builds up on its surface. This slide shows different views of our actual prototype. It has screws that will limit the leakage of the solutions from the flow chamber to the outside environment. And here you can see the outlet and the outlet, which is 4.8 millimeters. That's the actual thing. And this is the whole system set up with the coupling mechanism. Finding the Reynolds number. Finding the Reynolds number was very important in this project. And by using the velocity and density and the viscosity of the blood, also the diameter of the opening area of the mitral valve, we will be able to find the Reynolds number value, which is around 4,700. And this value is very high value. So we know that we will have a turbulent flow in the flow chamber, in our flow chamber. After calculating the Reynolds number, we determine the velocity using the thickness of 2 millimeter and the viscosity of the water and density of the water as well. And we got 2.11 meter per second. And this velocity is going to be inside the flow chamber, in the middle of the flow channel. And here you can see the inlet, the outlet, and the way through the chamber. How we choose our pump. We calculate the volumetric flow by multiplying the width times the height of the gasket times the velocity of 2.11, and we got our flow rate, which is 1.26 liter per minute. Our inlet velocity is 1.17 meter per second. This drawings, we got this drawing from the ANSYS. So this drawing shows the velocity distribution across the flow chamber, and you can see that the velocity is increasing, going from the inlet to the outlet. Here is the pressure distribution, and you can see that the pressure the actual pressure distributions will be like decreasing the pressure from the inlet going to the outlet. And that's much, like the ANSYS results much, very much our calculated values. Our flow chamber will have the following dimensions: 2 millimeter for the height, 30 millimeter for the length, 5 millimeter for the width. And these charts should be very small, because in case we may have to use the blood, so the dimension should be very small to minimize the need of the big quantity of the blood. This chart shows the solution go through to create a fully developed regions, and the distance between the inlet and the parabolic profile, which is the developed regions, is called the entrance length. This entrance length represents how far we have to go from the inlet to look for the builds up. To do good ANSYS analysis, we had to create a lot of planes to study the velocity magnitude at different locations. And these planes helped us to know where is the builds up gonna be. So we created 11 planes. The distance between each plane is 3 millimeters. The total length is 30 millimeters, which is the length of the gasket. So very much, it's like we create like 11 planes for the whole channel. These charts representing the velocity profiles charts for each plane. And you can see that the velocity profile started to become fully developed from plane 4, which is right here, to plane 8, which is right here. And then it's gonna disappear again. Where is it? Yeah. And then it's gonna disappear again. So you can see the that's it's parabolic, like the last the four lane and took 8. So very much we decided the entrance length is going to be something between 9 millimeters and 11 millimeters. And our interesting area, this will be between plane 4 and plane 8, which is 12 millimeters. That's the area we are going to test, and we will catch the particles through this area. These pictures setting up our systems and our chamber under the microscope to catch the particles and to measure the velocity of the particles through the flow chamber. Why we choose the dirt particles to test? Because the silicate particles were very expensive. It was something like 281 per gram, and the minimum amount we need is 10 grams, so it's going to be 2,000 something. So it's so expensive to get, and it's easily available, and the sizes of these dirt is very close to the sizes of the blood cells. And you can see here the dirt particle catched by the camera and with the microscope attached to the microscope. You can see the particles, the distance between particles here. We reduced our flow rate because of the microscope limitation. Couldn't catch a high flow rate of 1.26 liters per minute. So we decided to reduce it to 5 milliliter per minute. So we reduced it to 5 milliliter per minute. And these are the results of the testing. So we tracked 10 particles with the 3 different distances. And we have also the distance mean here. You can see the picture. There is the 4 points representing the first distance, second, third, and also the mean distance. And we calculated the mean velocity for each track. And the reason why here you can see the first track, which is the first particle, with the long distance, that's because this track 1, which is this particle, were very small. So that's why it went faster. And you can see like for each, but the mass ratio between them is it's not like a big deal. The total cost of our project is 181, inexpensive, and we are maintaining the maximum of 500. So we are good with the total cost. The schedule, our schedule, we done with the research, and also we done with the SolidWorks modeling. We successfully test our answers, test our chamber by using answers. We built our prototype successfully, and we done with the testing and the results. So very much we followed this schedule, and we followed everything in the fall and spring. In summary, we assembled a design which can be used under different lenses of microscope, different microscopic lenses, without any leakage, without any air bubbles, and we could catch the particles and measure the velocity of these particles and even the distances. So we very much create this prototype successfully. These are our references, and thank you. I'll be happy to answer any questions.
Yeah, you talked about putting in an air bleed. Something to take the air bubbles out. Can you talk about the design of that?
What's your question?
You talked about creating an air trap.
I didn't.
You mentioned that, but was there some design involved with that?
We didn't manage it. But actually, since we had very high flow rates in our
flow chamber, so we didn't have any bubbles inside the chamber.
I mean,
The only way I think to know is by looking using our eyes, and very much we couldn't find any bubbles inside, any air bubbles.
You also have a microscope.
Yeah, also we have microscope, and we couldn't see any kind of bubbles, air bubbles inside the flow chamber.
Go forward. One more. To the one that you showed the velocity profiles. That one. So, velocity distribution. You said that the velocity distribution increases as you go through the system.
that was actually what happens.
What happens to average velocity through the system?
Okay, we just found out that since we have very sharp edges in here, so what happens, we have very low velocity at the edges, right here. And if you look at every sharp edge, there is very low velocity.
Right. That's the local velocity, but what about
Yes.
average velocity?
Average velocity will be equalized in the both tubing.
Okay, so average velocity is the same throughout. Mass balance
Magnitude,
has to all.
yes. The integral of the,
Okay. Yeah, if you discover that average velocity changes, then you could get a Nobel Prize, right?
It changes from the flow chamber, but it's
actually the reason why we had that, that dark area in here, because we didn't apply much meshes in there. So we
Right.
had to redo it again yesterday, and very much we had good results.
Okay.
Question. What technique did you use to measure flow rate and velocity?
Actually, in the beginning, we had very sophisticated pump that's can be easily calibrated, and we borrowed that pump from Harvard University. So they want that pump back, and what we did, we just used the regular water pump, which is this one here. This one delivers 1 gallon per minute, and by passing it, so we were able to reduce the flow rate to 1.2 liters per minute. Very much what we did, we had this, we had like a bypass that can be adjustable, and then we just manually we were able to just using a timer to count how much flow we have in the container. That's what we did.
You just check time and then.
Just time in the container.
You knew the volume, so.
Correct. And that's what we did. That's one of the problems we faced
Did
actually.
you control velocity at different points, or you just measured average velocity?
Yes, at different points. We were able to do that, but the problem was because of the limitation of the microscope that we have in the lab, we were not able to catch such those particles in such high flow rates. So we had to reduce it just to show that we did some calculations.
How did you control velocity at each particular point? What tool did you use? What instrument?
Image Pro plus software.
Software?
Yes.
But technically, did you have some kind of prototype, physical prototype?
Yes, we
Yes,
do.
we have.
We have it
control
downstairs.
this, I don't mean just using software, but it's just practical.
Are you talking about controlling the velocity along the length or
No, across the cross section. Just, yeah. The cross section of this pipe. Just like parabolic, we show the parabolic.
Yeah, what we did was,
We use the Excel. We got the data from Axis and then we use it to Excel, and that's how we created this parabolic.
I saw that you showed the parabolic distribution of velocity.
yes, this is inflating the data like from every plane in here, and then very much by using Excel we were able to graph the position of each velocity what they call it,
versus the velocity?
vector, right, and then versus the velocity. We were able to get these. So very much with the help of this, we were able to discover that the flow becomes fully parabolic between 4 and the plane 8. And since the distance between each of these is 3 millimeters, so it's going to be 3 times 4, which is 12 millimeters. So very much, if we have chance to look for the build-ups on the under microscope, so we have to go in this area right here.
It's only 9 millimeters.
9 millimeters, yeah, 3, so 1
And the picture of, the picture of the actual, particles, yeah,
This one.
what are the green streaks?
These green states are the actual size of the different particles under the microscope.
So those are
And
the
they are in
particles, those are the
microscope.
reflections of the particles, is that what you're saying? And-
Oh, this is the size of the particles. Diameter.
So this is what the you use the automatic feature of the software, right?
No, it's
Why
not.
is it green?
It's green because these are the numbers
These
actually.
are numbers.
Oh, these are your
So,
numbers.
just you can see it here, but this represents the diameter of each particle. So, but you can see it, I don't know, for some.
But that green is, those numbers are superimposed by software, right? They don't look green under the microscope.
No, they
No,
don't.
they're not green. This is we type all these values, that's what we did. So just to get an idea about the, the app.
Okay, so
Okay.
we have to